Hello everyone. We came back with another lecture series, Advanced Semiconductor Diode. So in this lectures, we'll focus on working principles and construction of various advanced semiconductor diodes like Varactor diode, Avalanche diode, pin diode, tunnel diode, and Schottky diode, and we'll end up with the overviewing the applications of those diodes in various cutting edge applications. So before going to the Varactor diode, let us review the basics and fundamentals of the semiconductors, materials and their properties. We have covered in our previous lectures about the semiconductor diode. The semiconductor diodes, we know that this are the foundation of modern electronics because this semiconductor diodes is using everywhere, starting from our mobile charging to various household electronic appliance, and more or less we can say that in uh, every field, starting from study physical mathematical foundations and medical, defense or other applications, semiconductors are playing a very crucial role in electronic circuit and system. So they are very much essential for alternate current, direct current conversion, voltage regulations, and signal processings. They are whatever the ongoing innovations in diode technology, they are driving very advancements. The semiconductor diodes market is projected to reach around 1000 billion by 2030. So semiconductor is a very fundamental backbone of the modern technology, modern electronics, we can say. So let us see that what are those semiconductor diode. So semiconductor diode is nothing but it is a two-terminal device, and it conducts current primarily in one direction. And semiconductors is basically have various form. Intrinsic, we categorize as intrinsic or extrinsic semiconductor. Intrinsic or pure semiconductor, there we are not doping any kind of materials. So like we know that very familiar and very famous example of intrinsic semiconductor like silicon, germanium. So basically at room temperature, the thermal energy excites electron across the band gap. It generates electron hole pairs, and carrier concentration, basically the in intrinsic semiconductor, hole carrier concentration and electron carrier concentration are same. In other side, the extrinsic semiconductor we create intentionally by adding some impurity, or we can say by adding the doping. So based on our wishes to apply them in various application, we dope the material. So depending on the type of doping, like we have covered in previous lecture in detail, so let us just briefly say n type are the donor atoms. If we dope the phosphorus in silicon, that means we are adding electrons. And p-type semiconductor, those also called as acceptor atoms. If we dope the boron in silicon, it will create the holes. So likely uh, that we differentiate n-type and p-type based on their majority charge carriers. So in n-type semiconductor, the electrons are basically the majority charge carriers and holes are the minority carriers. So for case of p-type, the holes will be the majority carriers and electrons are the minority carriers. So when these two p and n-type materials sandwich, basically then form the PN junction. So in the doped semiconductor, the examples are gallium nitride, silicon carbide, etc. These are the key materials for the semiconductor diodes. So in PN junction diode, it creates when two N and P type material sandwich, they will create a deflection region. Forward and reverse bias conditions create the current flow. Doping concentration or doping percentage will mainly affect the forward voltage and breakdown voltage. So basically due to the diffusion, that means electrons from N side and holes from the P side move to other side due to concentration gradients, and next step will be the recombination. This occurs when they meet and leaving behind the ionization atom, that is fixed charge. So, and deflection region, this is basically nothing but a region devoid of mobile charge carriers formed by recombination and fixed ion charge. And this creates an electric field pointing from N to P, or establish the equilibrium, like diffusion current will be equal to drift current. So they will create the built-in potential, and typically the built-in potential for silicon is 0.6 to 0.7 volt, and it will prevent further diffusion. So how this diodes is work, just that what is the difference between forward and reverse bias? The forward bias basically the low resistance, obviously majority current will flow, the current flow when positive charge is applied. So for this silicon it is around 0.7 volt, and reverse bias basically the current flow due to the minority carriers. So here it's the resistance will be very high, very minor current flow until breakdown voltage is reached, and this reverse breakdown reverse leakage current basically increase exponentially with the temperature. So actually the semiconductor materials behavior, temperature have a very crucial role or very effect in their properties, so basically show two point is here, that in the forward bias here the external voltage reduces the barrier height and then increases the injection of the majority carriers. As a result, the large amount of current can flow with forward bias condition, and on the other hand in the reverse bias condition basically increases the barrier height and it wide the deflection region. So as a result only small leakage current flows. So if we summarize this PN junction diode or junction materials, that is basically the core of most of the diode. The charge free region or set built-in potential, that is the depletion region. Carrier dynamics driven by diffusion plus drift, and capacitance varies with the bias, crucial in high speed apps, and its real effect is in resistance, series resistance, leakage, breakdown voltage, breakdown region, and it have a effect temperature. So let us that why those diodes are very much important, as we mentioned that it used in various modern age applications like power supplies convert AC to DC, and power it will be used for power supply converting AC to DC. 90% plus of power supply uses diode only. We are very popular with the LED lighting. So this is basically nothing but the light emitting diodes. Those are very efficient and long lasting lighting, and even very cost effective. And another very important perspective is in solar panel. We will come back with another lecture series about the solar panel in our next lecture series. Diodes prevent reverse current flow at night. Means solar panel basically depends on the sunlight. So daytime we can store it in the form of electricity with semiconductor diode, because semiconductor diode have very good capacity to absorb the light, and then we can use in the night time while there is no sunlight. And automotive electronics used in voltage regulation, lighting, sensing, and various other applications. So let us first start with the diode series. First is the Varactor diode. So we'll be focusing on the principle, construction, and working of this Varactor diode. So basically these diodes are Varactor, pin, Avalanche are very special type of diodes for particular some applications. So what change in the structure and materials result various different behavior, and why they are used, and uh, where they used. Okay, so we'll be focused in our this lecture and all these points. So diodes we already summarized it, that semiconductor based component that allow current in one direction and block in other direction. There are several types of diode used in various circuits. So Varactor diode is basically a type of diode that will be discussed in this section in details. So Varactor diodes, this we can see that this is the symbol of the Varactor diode, the specialty of this diode, and we'll be focusing on its IV characteristics. So we can understand from here that this symbol is basically these capacitors, and this is nothing but a diode. So this is kind of linked that this diode could be used as applications or for capaciting purpose. So let's explore it. So Varactor diode is a PN junction diode whose capacitance is very varied by varying the reverse voltage. So before going to the Varactor diode, let us look on the what is the capacitors. So a capacitors is an electronic component that store electrical energy or electric charge in the form of electric field. So the basic capacitor actually basically made up of two parallel conductive plates separated by a dielectric media. The two conductive plates acts like a electrode, and dielectric is basically uh, acts as an insulator. So as we said that two conductive plates, so this conductive plates is positive charge and this side is the negative charge. So these conductive plates are, we know that they are very good conductor of electricity, so they easily allow electric current through them. On the other side, the dielectric are the very poor conductor material. So dielectrics have the very poor conducting, uh, poor, we can say the poor conductor of electricity. So it doesn't allow electric current through it, but it allow electric field or electric forces. So when we applied the voltage, applied the voltage to the capacitor in such a way that the negative terminal of the battery is connected to the suppose let us see that this positive terminal of the battery is connected to the left side of the electrode, and negative terminal is connected with the negative part of the battery is connected to the this side, negatively charged this plate. So what will happen that if the voltage is applied in this way, that negative terminal of the battery is connected to the right side of the electrode on or plate, or positive terminal is connected to the plate of left side. The capacitor starts storing the electric charge, because because of this applied voltage, a large number of electrons start flowing from the negative terminal of the battery through a conductive wire. When these electrons enter into the right side of plate, a large number of atoms in the right side of the plate gains extra electron. So we know that any object that has a large number of electrons nothing but the that negatively charged carriers, then the protons positively charged carrier is said to be negatively charged. The right side of the plate has a large number of electrons than protons. So right side plate becomes the negatively charged because of gaining of extra electron. The free electrons of this negative side of plate or electrode will try to move into the dielectric. However, dielectric blocks this electron. So what will happen? As a result, a large number of electrons are built up on the right side of the plate. Thus, right side of the plate becomes the negatively charged electrode. The dielectric blocks flow charge carrier, that means free electrons, but allow electric forces exerted by negatively charged electrode. Similarly, the electrons of this left side of the plate experience a strong attractive force from the positive terminals of the battery. As a result, a large number of electrons leave left side of the plate and flow towards the positive terminal of the battery terminal. So ultimately the positive charge is accumulated on the left side of the plate. These positive and negative charges accumulated on both plates exerted force on each other. This force is basically the attractive force between the plates, and it is nothing but the electric field between the plate. So as we know, the capacitance is the ability to store the electric charge. So at both plates, the charge is stored. Thus, exists a capacitance at both plates. So, so this is now clear that capacitance, we know that it have a ability to store electric charge. So both plates will be stored the charges, and thus there exists a capacitance in the both the plate. So now look that what is the Varactor diode. So it is basically it's originate from the variable capacitors. Varactor diode operates only in reverse bias, means manufacture this diode in such a way that it will operate in the reverse bias. The Varactor diode acts like a variable capacitors under reverse bias. So this diode actually is also called as varicap diode, tuning diode, variable reactance diode, or variable capacitance diode. So this Varactor diode is referring mostly with the name of varicap diode or turning diode, variable capacitance diode. There are various alternate names of these diodes. The Varactor diode is manufactured in such a way that it is better transition capacitance property than the ordinary diode. So let us see how this diode construct. That as we already know, that Varactor diode is made up with a p-type and n-type semiconductor. So p-type materials, here we can see uh, that there will be majority of the holes, and for the n-type material there will be the majority of electrons. So in n-type semiconductor, the free electrons will be act as a majority carriers and holes will be act as a minority carriers. So the free electrons carry most of the electric current in the n-type semiconductor, and in p-type semiconductor the holes are majority carrier and free electrons are basically the here the this electron. So holes carry most of the electric current in the p-type semiconductor. So when both p and n junction has sandwich, basically they will form a junction, and near to the junction there will be here defined by dotted line is create with the deflection region, and in this region is basically a region where the mobile charge carriers, these free electrons in holes are present. So since this is the p-type material, near to the p-type material here will be the negatively ions will be dominating, and for n-type here will be the positively ions will be dominant. So this deflection region also made up with positive and negative ions. The positive and negative ions does not move from one place to another place. This deflection region also block the free electrons from n side and holes from p side. This deflection region blocks the electric current across the p-n junction. So this is the typical symbol of the Varactor diode. So this is basically the diode and anode cathode, and towards the cathode there is two parallel line, as it is shown as parallel capacitors. So two parallel lines at the cathode side represent two conductive plates, and space between these two parallel lines separates dielectric. So let us see now that how this Varactor diode do the biasing and bias condition and unbiased condition. So we know that as n-type semiconductor, a large number of free electron presents, and in p-type semiconductor a large number of holes are present. So free electrons and holes always try to move from a higher concentration region to lower concentration region. For free electrons, n region is the higher concentration region, and for p region is the lower concentration region. For holes it is opposite, that means p region is the higher concentration region and n region is the lower concentration region. So therefore free electrons always try to move from n region to p region. Similarly, holes always tries to move from p region to n region. So when no voltage is applied, a large number of free electrons in n region get repelled from each other and moves toward the p region. So basically when this free electrons reaches this p-n junction, they experience an attractive force from the holes in the p region, As a result, free electron cross the p-n junction, and similar way holes also cross the p-n junction. Because of the flow of this charge carrier, because of the flow of this charge carrier, a tiny current flow across the diode for some period, some certain time. During this process, some neutral atom near the junction in N side loses electron and become positively charged atoms, or we can say the positive ions. Similarly, some neutral atoms near the junction at p side, they will uh, they will gain extra electron and becomes negatively charged atoms, that is the negative ions. These positive and negative ions creates at the p-n junction is nothing but deflection region. This deflection region prevents further current flow across the p-n junction. So this actually this width of this deflection region depends on the number of impurities added, that is amount of doping. So it's again depends on our manufacturing, means depends on our application or type of purpose we are going to use. So a heavily doped Varactor diode has a very thin deflection layer, whereas lightly doped Varactor diode has a wide deflection layer. So we know that an insulator or dielectric doesn't allow electric current through it. The deflection region also does not allow electric current through it. So the deflection region acts like a dielectric of a capacitor. So we know that electrodes or conductive plates easily allow electric current through them. The p-type and n-type semiconductor also easily allow electric current through them. So p-type and n-type semiconductor acts like the electrodes or conductive plates of the capacitor. Thus, Varactor diode behaves like a normal capacitor. So in unbiased Varactor diode, the deflection width this is very small. So capacitance or charge storage will be very large. So in unbiased conditions, the Varactor diode behaves like a normal capacitor. So this is very important to note that in unbiased Varactor diode, deflection width is very small and resulting high capacitance. So how the operation is occur in the Varactor diode, how Varactor diode works. The Varactor diode always, as we shared in introduction, that Varactor diode is always operated in reverse bias, because in reverse bias the electric current does not flow when forward bias voltage or forward bias voltage is applied. The electric current flows through the diode. As a result, the deflection region becomes negligible. We know the deflection region consists of stored charges. So stored charges will become negligible, which is undesirable for in this case. So Varactor diode is designed to store the electric charge, not to conduct electric current. So Varactor diode should always be operate in the reverse bias. So when this Varactor diode, so this is actually, you can see that this is p-type terminal and the battery's negative terminal is connected with the p-type and N side is connected with the positive terminal of the battery. So this is basically the reverse bias connection. So when we connect in the reverse bias, the electron from the N region and hole from the P region moves away from the junction. this junction. As a result, the width of the deflection region is increased and the capacitance is decreases. So if we so this is basically the typical reverse voltage with the capacitance nature of the Varactor diode. So capacitance decreases when the reverse voltage increases. The capacitance slope, you can see that it is gradually decreasing while we are increasing the reverse voltage. So when the this applied bias voltage is very low, the capacitance will be very large. So low reverse bias voltage give the high capacitance, and high reverse bias voltage will give the small capacitance. So this is very important to remember for the Varactor diode, that in the reverse bias condition, while we are applying very low reverse voltage to the system, the capacitance will be very high, and while we are applying the very high reverse voltage, the capacitance or amount of charge storing will be very less. So if we frame a consequence with this capacitance and applied voltage, that the capacitance is inversely proportional to the width of the deflection region and directly proportional to the surface area of the deflection region. So if we see that here, that from the picture it is clear that low reverse bias voltage, that this deflection region is very narrow. That means here less, it is denoted with this dotted line, and here it is width of the deflection region is very wide. Then here is a very high reverse voltage and small capacitance we are getting. So the capacitance decreases as the width of the deflection region increases, and we can summarize it as that if reverse bias voltage is increased, the width of the deflection region further increase and the capacitance further decrease. Or if the reverse bias voltage is reduced, the width of deflection region decreases and the capacitance increases. Thus, an increase in reverse bias voltage increases the width of the deflection region and decreases the capacitance of Varactor diode. The decrease in capacitance means the decrease in the storing of the charge or storage charge. So the reverse bias voltage should keep at a minimum to achieve large storage charge. Thus, the capacitance or transistor capacitance can be varied by varying the voltage. So, in a fixed capacitor, the capacitors will not be varied, whereas in variable capacitors, since we mentioned that Varactor diode is used as a variable capacitors, the capacitance is varied. So in a Varactor diode, the capacitance is varied when voltage is varied. So Varactor diode is a variable capacitors. The capacitance of the Varactor diode is measured with the picofarad, and the voltage is in volt only. So now let us see that what are the applications of Varactor diode where we can use the Varactor diodes and what are its advantages. So mainly if we classify with the um, major application part, so it can be used for voltage controlling or voltage control oscillators. It can be used as electronic tuning and the parametric amplifier. So if we look with the voltage controlled oscillators, that here Varactor diode is used in phase locked loop in communication system, and in the uh, electronic tuning it can be used as a TV tuners or radio receivers in FM radio range. So it also used in various frequency multi multipliers. Vector dash is also used in parametric amplifiers. It like low noise amplifiers or used in radio astronomy, is also used in satellite communications. So this Varactor diode basically have the advantages is that it electric control, compact size, and high reliability. In same page, this Varactor diode is very sensible in the temperature, so it limiting the capacitance range and sensitivity to the temperature. So this is the advantage of this Varactor diode. So just to elaborate its application, let's see that how this Varactor diode used in tuning circuit. That Varactor diode application in tuning circuit. So it used actually, we know that Varactor diode is used in tuning circuit to adjust the resonance frequency of the circuit by varying the voltage. So here this schematic of this tuning circuit is given. So basically, we know that in LR circuit, that means one resistance, one L inductance. This is basically R, L, and C. We are using here this diode along with the capacitance. So basically, in the RL circuit, that when we add two Varactor diodes, so D1 and D2 with the two Varactor diodes with the variable capacitor C1 and C2, a resistor R and a inductor L. The two diodes are connected in reverse bias. That is, their cathode are connected with the variable positive uh, DC voltage supply. The variable DC voltage is used to vary capacitance of both diode. Therefore, the total capacitance, that is, if we define CT, so it is basically the CT is basically the combined capacitance of both the diodes. So if yes, we know the formula for resonant frequency is this F naught is equal to 1 upon 2 pi root over L CT. This CT is nothing but the combined capacitance of both the capacitors. So CT is basically C1 C2 divided by C1 plus C2. F naught is the resonant frequency. L is the inductance measured in Henry unit, and CT is the total equivalent capacitance of both the diode. So this is basically up to here is the Varactor diode, how it work, how is construct, what are the application and advantage and disadvantage. In the following section will be move for the second another type of special diode, that is the avalanche diode. We will be focusing in this section the avalanche diode. What is this diode, how it work, we'll see. So avalanche diode is basically a special type of semiconductor device designed to operate in reverse breakdown region. Avalanche diode are used basically in the relief valve, that a type of valve where used to control the pressure in a system to protect the electrical system from the excess of voltage. So key point that it is a high speed high voltage semiconductor device designed to operate in a reverse breakdown region. It uses as mentioned the relief valve, and it actually have very fast resonance time and soft breakdown voltage. And this is the basically the symbol of Varactor diode. So that in this side, this lines is slightly, it is not the completely slipping line, it is just bit curved. So now let us see that and that how the Varactor diode is operate. That this diode is diodes rely on impact, ionization, and avalanche multiplication. A large reverse voltage create a strong electric field. Then accelerated electrons collides with atom, generating electron-hole pairs. These newly freed carriers accelerate and cause further ionization. Precious doping profile ensure control breakdown. So if we stepwise define it, basically high reverse voltage, and as a result it will create the strong electric field. Impact ionization, so as a result the electrons collide with the atoms. And third is the chain reaction, rapid current increase. So this is that how to work, or in which principle that avalanche diodes work. So let us see that what is its construction mechanism. So avalanche diode are as generally made from the silicon or other semiconductor materials. The construction of this avalanche diode is very similar to the Zener diode, which work as a voltage regulation, but the doping level of the avalanche diode is differ from the Zener diode. So first is the avalanche diode features is uh, heavily doped P plus and N plus region. They operate an intrinsic or lightly doped region. Structure like PIN means intrinsic, P is P-type, intrinsic and plus are optimized for avalanche effect. Intrinsic region with is precisely controlled to set the breakdown voltage. So basically avalanche diode is lightly doped, therefore the width of the deflection layer is in avalanche diode is very wide compared to the Zener diode. Because of this width, the deflection region and the reverse breakdown occurs at high voltage in avalanche diode. The breakdown voltage of avalanche diode is carefully set by controlling doping level during manufacture. So as I beginnings mentioned that all the special diodes are made from that semiconductor materials, but while we are manufacturing, depending on the manufacturing doping level, it has defined as different types of diode for various applications. So basically, if we construction divide, so it basically we can categorize in three parameters like doping region, intrinsic region, and the metallization. In doping region, we heavily doped P and N region. Intrinsic region, the width control the breakdown voltage, and metallization is ohmic contact in between P and N. So this, as we mentioned, the region is very wide. These are the negative ions, these are the positive, and this junction formation deflection region properties or how they work we have discussed during the Varactor diode series. So I am not going for that. That here in p-type, that free electrons hit the atom at high speed, and then the new electron hole pair is generated. and you can see here that width of deflection region for this avalanche diode is very width. So this avalanche diode, as we discussed in this previous slides, that its symbol is very similar with the Zener diode, but it is it like normal diode, it have the two terminals, anode and cathode, but bondage up towards the bondage is bit vertical lines. So now we'll move that how this avalanche diode work. So this is basically the typical IVFVI characteristic voltage with the current characteristic avalanche diode. So this blue line is basically the IV characteristics of for avalanche diode, and this red, this part is kept as a reference with the Zener diode. So basically in this diode, that we know that for normal PN junction diode that allow electric current only in forward direction, where is the avalanche diode, avalanche diode allows the electric current in both forward and reverse condition. Actually, if we see that for normal diode, actually this slope is very close to here, means this reverse bias is very less, because you know that in the normal diode the reverse current is due to the minority carriers. So this avalanche diode allow the electric current in a reverse condition. When the reverse bias voltage exceeds the breakdown region, the point, or here this point, or this point, here the point at the voltage where the electric, this is basically denied Vz is the general breakdown voltage, or for avalanche this is this Br. So when the current is suddenly increases, this is called the breakdown voltage. So when the reverse bias voltage applied for the avalanche diode exceed the breakdown voltage, a junction breakdown occurs. This junction breakdown is called the avalanche breakdown. So when forward bias voltage is applied to the avalanche diode, it works like a normal diode by allowing the electric current through it. So when reverse bias voltage is applied to the avalanche diode, what happens? Basically the free electrons, that means majority carriers in the N-type semiconductor, and holes, that is majority carriers for P-type semiconductors, are moved away from the junction. As a result, the width of the deflection region is increased. So therefore the majority carriers will not carry the dielectric current. However, the minority carriers, that is free electron in p-type and holes in n-type, experience a repulsive force from the external voltage. So in the forward bias, basically the current start around from zero point 0.6 to 0.7 volt, and then increases exponentially. This is standard PN junction diode behavior. For reverse bias, the small current, leakage current is there before the breakdown region reach. Once it reaches to breakdown voltage, that is here, the current is vertically, the sharp vertical current, you can see this spike. So this is called actually the avalanche effect, sustains high current safely. So the breakdown voltage, the higher than that of the Zener diode, means avalanche diode also working as a reverse breakdown voltage, and it also have a very similarity, but the avalanche diode, the breakdown voltage is much more than the Zener diode. Actually that in the for avalanche diode, that if we apply the reverse bias voltage, the avalanche diode is further increasing, and the minority carriers, that is free electrons or holes, will gain the large number of energy and accelerate to greater velocity. The free electrons moving at high speed will collide with the atoms and transfer their energy to the valence electron. The valence electron, while they gain the enough energy from high speed electron, will be detached from the parent atom and become the free electron. These free electrons are again accelerating. When those free electrons again collide with the other atoms, they knock off more electrons. Because of this continuous collision of with the atoms, a large number of minority carrier, that is free electrons or holes, are generated. This large number of electrons carry excess current in the diode. So while we are applying this reverse voltage, and at some point this junction breakdown is occurred, or we can say that avalanche breakdown occurs, at this point actually is very small increase in voltage suddenly increases the electric current. This sudden increase of electric current may permanently destroy the normal PN junction diode. However, the avalanche diode may not destroy because they are carefully designed for uh, to operate well in this avalanche breakdown region. This breakdown voltage of avalanche diode depends on the uh, doping density. Increasing doping density will increase the breakdown voltage of the avalanche diodes. So avalanche diode actually have various application. It can be used in noise generators. Diodes are used in the protecting circuit. So if we highlight its application in it can be used at transit voltage suppression, that is TVS, transit voltage suppression, ADS, that electrostatic discharge, or pulse generator. Also it also used in optical communication receivers, and actually this avalanche diode is offer very fast, reliable over voltage and over voltage protection. However, it have the similar disadvantages like Varactor diode, that this diode means defining that doping concentration is a very crucial point, or very means, and it have a very sensitive in the temperature, so temperature sensing is there. So else this avalanche diode is very useful in TVS, EDS and pulse generator, this kind of applications. So in our next part of the lecture, we will move for next another diode that is called as the pin diode. So basically it is also one of the unique semiconductor diode, builds on conventional PN diode by incorporating additional layer. Here actually rather the doping percentage of manufacturing this diode is important is incorporation of a additional layer. If we see that suppose this is our one layer and this is the P and N1, in between there you can see here as mentioned as green yellow, so this is another. So basically we know that PN junction is a sandwich between one P and one material, but for pin diode in between P and A there will be one additional layer. So that is the speciality of this diode. This is, we can say that, unique semiconductor diode with an additional layer, making it a three-layer structure. and it consists of a p-type semiconductor layer, an intrinsic, that is undoped layer, and an n-type semiconductor layer. Hence the name is PIN, means P is coming from p-type, I is coming from intrinsic, and N is coming from n-type. This intrinsic layer is basically mostly made of pure silicon or germanium. This layer is highly resistive and enhance the diode performance significantly. The pin diode pin that if we this is the basically the pin, that means one p layer, and in between p and an intrinsic layer, and the symbol of pin diode is looks similar like PN junction diode, but there have arrow this point from the anode to cathode like a regular diode, means except this line it is looks like very similar with the PN junction diode. So this is the identification symbol or identification mark for this pin diode. So the symbol of pin diode is includes a stable distinction to reflect its unique structure. This standard diodes, this arrow point is not available, but there have this bar is there for normal PN junction diode, and this is actually signifying that presence of the intrinsic layer. And if we see that how this how this pin diode is manufactured, in this way it is manufactured, this p side and not p region made, n region made with this cathode, and in between there is the intrinsic layer. This manufacture involves mainly diffusion and epitaxy method. So let's discuss that how we can construct the pin diode. So this we know early very well that this is made of with a three different layer P and a undoped or intrinsic layer. So basically the pin diode is constructed from three distinct semiconductor layer: P type, an intrinsic layer, and an N type. Intrinsic layer, as already mentioned, that it is basically made of from silicon or germanium, and it is basically sandwich between P and N type. In main manufacturing method, basically use the one is the use in metastructure, another is the plane structure. So what is metastructure? Basically when the P and N layer are grown separately on the intrinsic layer to minimize the carrier recombination, resulting lower resistance and capacitance. And the planar structure means, that means like that where the thin P and N layer are deposited on either side of the intrinsic material. So this planar method basically optimize the diode for high speed, high voltage performance. So pin diode could be manufactured or can be constructed in two way: metastructure, while we'll be using for low resistance and capacitance, and another place is when we'll use this for high speed and high voltage performance, we'll go for the planar structure. So this is the just difference of two way to make it structure of this diode, depends on the applications. So this pin diode basically working is very similar like the normal PN junction diode. So but obviously since here have intrinsic layer, this intrinsic layer is profoundly influence uh, for their working. So basically when you don't apply any bias in pin diode, the P contains, we know that hole, N region contains the electrons, and the intrinsic layer acts as an insulator barrier with no net charge carrier. So it will prevent the current flow. In forward bias, applied voltage pushes hole and electrons towards the junction, initiating deflection region, allowing carrier to float the intrinsic layer and recombine. So it will initiate current flow. A large intrinsic layer requires a strong electric field to inject carriers, enhancing their speed and reducing resistance. Resistance decreases as voltage increases, making diode a variable resistor. In reverse bias, the voltage pulls carry away wide the deflection region across the intrinsic layer, and this blocks the current, and P and N layer store charge like capacitor plates. Intrinsic layer will be act as a dielectric, yielding that it can use as a capacitance. So this makes superiority of the spin diode to use as an effective switch or capacitors in the reverse bias. So let us see its characteristics. So this is the typical IV characteristics of PN diode. It plotted current versus voltage both in reverse bias and forward bias. In the forward bias, basically the electron and hole, as told, then enters the intrinsic region, charge build up module forward resistance. So this forward bias, this diode can work as a variable resistor. So this is the resistor symbol, and in arrow mark of the resistor symbol is indicating that this is the variable resistor. That means we can change the resistance. So in this junction there is an electric field that has the large strength due to the speed of this transportation of charge increases from P to N region. On the other hand side, if we see in the reverse bias condition, that up to this breakdown voltage VBD, that this current is very low, and after this breakdown voltage current is increases very sharply. So here basically the deflection region is expanded a lot, increases with the reverse voltage. At certain voltage all the charges in the intrinsic layers, and this is called the sweep in voltage. So basically the sweep in voltage for this pin diode is of around -2 volt. And since in this reverse bias voltage, this voltage pulls carrier away, it widening the deflection region across the intrinsic layer, the blocks current P and N layer, storing the charge like capacitor plate. So this intrinsic layer act as a here, the intrinsic layer of the pin diode here act as a dielectric, yielding capacitance. That we know the capacitance formula is C is equal to epsilon A by omega, where that epsilon is the permittivity and A is the junction area and W is the deflection region. So this makes the pin diode as the effective switch or capacitor in reverse bias. So we can say that in the reverse bias voltage, uh, this can be work as a capacitors. So it has a dual it reflecting this IV characteristics dual behavior, that in forward bias this diode can act as a uh, variable resistors, and reverse bias it can act as a reverse bias, it can act as a capacitance. So basically we can this voltage amount actually in the forward bias that around 1.4 volt higher than a typical PN diode due to this intrinsic layer width. As voltage is rising to high, this showcasing this variable resistance nature. So this is the VF, and so we can say that forward bias, that there will be no current. This region we can see that it is slipping line along with this voltage axis, that this is around 1.4. Typically it is for pin diode 1.4, and this is very high than the normal PN junction diode. Normal PN junction diode, basically this is very less, like 0.5, 0.6. Then this is rising very sharply, resistance drops. And the reverse bias, we can see that very small leakage current holds to speed up to breakdown. So this breakdown voltage is actually very high, like 400 volt. Suddenly current surge, higher breakdown voltage than the very high due of the PN junction, due to PN diode have very wide deflection layer. So basically forward curve shift, this we say that reverse current is beyond this, before this spike. This part is very similar like the normal PN junction diode. This part. So this is very special kind of diode, that at same time it's from the same die, different forward and reverse characteristics we are getting as variable resistor as well as the capacitors. So now let us look its application. Majorly it used in RF switch. It also used the variable attenuation control, and also it used as a photodetector devices. Photodetector is also one kind of optoelectronic devices. It have various advantages, that it perform very exceptional oil at high frequency because of reduced capacitance and fast carrier movement. It can block or handle very high reverse voltage, making it robust for power applications. And also it has a very fast photosensitive because of this intrinsic region. So it is enabling to use diode, this converting light into electric current. So that's why it is using as photodetector. It reverse breakdown voltage is very minimal, that is enhancing efficiency, and it serves as a variable resistors in forward bias with very low noise output. So these are the very useful features of this diode. In the next part of the lecture, we'll move for the tunnel diode. So basically this tunnel diode is due to its nature in characteristics, the tunneling behavior, it named as tunnel diode. It's very interesting and very efficient one of the diode, this tunnel diode. So let us move for tunnel diode. So it is basically a very heavily doped PN junction diode made of, means basically in general, gallium arsenide, germanium or silicon. Doping percentage or doping concentration while manufacturing is very high, as that normal diode, if we compare, it is around 1,000 times higher, more than 1,000 times higher than normal diodes. Generally these diodes are manufactured in diffused junction method or epitaxial growth, and this hermetic sealing is used for stability in packaging. So if you just um, point out the brief of that what is tunnel diode, then we can say that it is a very heavily PN junction diode in which the electric current decreases as the voltage increases. In tunnel diode, basically the electric current is caused by tunneling. The it is used very fast switching device in computer. It also used in very high frequency oscillator and amplifier. So this is the typical symbol circuit symbol of tunnel diode, and so we can see that it as say that all are the made from the diode, so it have two terminal, anode and cathode, but depends on their properties, it identifying mark or symbol is different. So here you can see that from normal diode, this line of cathode is towards the anode, two lines, straight lines. So basically we know that the anode is positively charged, and that means it will attract the electron, whereas the cathode is negatively charged electrode that emits electron. So in tunnel diode, actually the n-type semiconductor emits or produce electron, so it is referred to as cathode. On the other hand, the p-type semiconductor attracts electron emitted from the n-type semiconductor, so p-type semiconductor is referred as the anode. So how it named with the tunnel diode? So if we go back to the history of the tunnel diode, that it is one of the most significant solid state electronic device which have made their appearance in the last decade. Tunnel diode was invented in 1958, but Schottky diode. So it is named after the Leo Isaacsy for his work on tunneling effect. So basically, what this scientist Leo observed that scientist Leo observed that if a semiconductor diode is heavily doped with impurity, it will exhibit negative resistance. Negative resistance means nothing but the current across the diode decreases when voltage increases. So in 1973, this scientist Leo received the Nobel Prize in Physics for discovering this electron tunneling effect used in this diode. So a diode, tunnel diode is also known as that Schottky diode after after his name, like Leo Isaacsy, on the tunneling effect. So the operation of tunnel diode depends actually quantum mechanics principle known as tunneling in electronics, and the tunneling means a direct flow of electron across a small deflection region from n side conduction band into p side valence band. So important point is that is defining this tunnel diode name due to this tunneling effect, and in electronics we are meaning this tunnel is the direct flow of electron across the small deflection region from inside conduction band into p side valence band. So the the germanium material is commonly used to make the tunnel diode, and they are also made from other like gallium arsenide, silicon, or germanium. So since here for the tunnel diode have a very crucial role or effect of depletion layer. So let us see that what are the width of deflection this region in tunnel diode. So the depletion region in a PN junction lacks mobile charge carrier. It acts as a barrier to electron and hole flow, and this width of depletion region depends on basically the number of impurities added. So we know that impurities are the atoms that introduce into the P or N type of semiconductor to increase the electrical conductivity. So purpose of the doping or impurity is nothing but the increasing the electrical conductivity. So if a small number of impurities added to the PN junction diode, means normal PN junction diode, then wide depletion region is formed. On the other hand, if a large number of impurities added to PN junction diode, a narrow depletion region is formed. So for case of tunnel diode, that both sides are heavily doped. So it causes that, as we know that if we doping very heavily, then this layer thickness or width will be very narrow. So for case of tunnel diode, both P side and N side are very heavily doped, so that this deflection layer is very thin, or we can say very extremely narrow deflection region is forming. And it's this impurity concentration is basically, if we compare with the normal PN junction diode, it is more than 1,000 times of the normal PN junction diode. So in normal tunnel diode, basically uh, this P and N both, while the very heavily doped, means a large number of impurities we are introducing, then we are getting extremely narrow depletion region, and this causes that when we apply very small voltage, that very small voltage is enough here for produce electricity in tunnel diode. This tunnel diode capable of remaining stable for a long duration of time than the normal ordinary PN junction diode. And also this diode is because of this depletion region with is high speed operation. So why not for normal diode? Because in the normal diode the depletion layer is comparatively large than the tunnel diode. This width of the depletion layer or depletion region in normal diode opposes the flow of current. Hence the depletion layer acts as basically the barrier. So to overcome this barrier, we need to apply sufficient voltage, and when sufficient voltage is applied, the electric current starts flowing through the normal PN junction diode. So let's see that what is the main concept of tunneling. That depletion layer or region is in PN junction diode is basically made of we know that positive ions and negative ions. Because of these positive and negative ions, there exists a built-in potential. So and next, this if there is a built-in potential, then what will happen? This electric field in the depletion region exerted electric forces in a direction opposite to the external electric field, or we can say that external electric voltage. So that means that this electric field opposes the external voltage applied to the diode. So another important thing is that we need to remember that the valence and conduction band energy levels in p-type semiconductor are slightly lower than the valence and conduction energy band level in p-type semiconductor. This differences of energy level in p and n-type semiconductor is due to the difference in the energy level of this dopant atom. That means and that donor and acceptor atoms uh, used to form this p and n type of semiconductor. So this p-n junction diode, this energy band of that is means energy band is nothing but the difference or gap between the valence and conduction and valence band. So in n type slightly lower than those of the p type. So the energy difference actually this comes from the dopant atom and used in each semiconductor like N type and P type, that donor and acceptor atoms. So this causes the this causes the difference between normal to tunnel diode behavior or tunneling effect. So let us just look a overview that how electric current flow or electric current is produced in normal PN junction diode. Basically, this is the normal forward bias PN junction diode structure. So when we apply the forward bias, what will happen? The width of the deflection region is decreased, and at same time the barrier height, that means if we define in this way, this barrier height will also decrease. However, so we can see that these electrons pass over this barrier, then has to come in the p side. So this height, if you define, we can say that here these are the electrons is there. If they want to come here, they has to cross it in bigs. Means they has to jump this barrier, then can come. So electron in the n-type semiconductor cannot penetrate through deflection region because built-in voltage of this layer opposes flow of electron. So in ordinary junction diode conducts current only when applied voltage exceeds the built-in voltage of the deflection region. So if the applied voltage is greater than the built-in voltage in normal PN junction diode, the electrons from inside overcomes the opposing force from deflection layer and then enter the P side. In simple word, we can say that electrons can pass over the barrier or deflection layer if energy of the electron is greater than the barrier height or barrier potential. So in PN junction diode produces electric current only if applied voltage is greater than building voltage of this barrier region or deflection region. So now move for electric current flow for the tunnel diode. So in tunnel diode, we know that valence and conduction band energy level, that p-type semiconductor is n-type semiconductor is lower than the p-type semiconductor. You can see here that if we see this EC stands for conduction band of N side. EC, it is conduction band of P side. EV, this is valence band for N type, and this EV is the valence band or valence energy level for P type or P side material. So you can see from this diagram that this is bit high than this is. So we can say that both conduction band and valence band energy levels of N-type semiconductor are lower than the valence band and conduction band energy band of N-type semiconductor. Unlike the ordinary PN junction diode, the this difference, this energy difference in between energy level difference in between P and N type semiconductor is very high in tunnel diode. Because of this high difference in energy level, the conduction band of N type material overlaps with the valence band of the P type material. Because if we look the barrier, the height, that conduction band of the P type and conduction band of P type and conduction band of the N type is so high, but nearer to this energy level is the valence band of the P type. So the electron tunnel through the barrier can come here, electron to here, because this is very close to each other, and you can say that this is overlapping with the valence band of the P type. And we know that quantum mechanics tells us that the electron will directly penetrate through deflection layer or barrier if the deflection width is very small. So the deflection layer of tunnel diode is very small. It is in, if we say it is in very small in the sense, if we range it, like it will be range in the nanometer. So the electrons can directly tunnel across the small deflection region from inside conduction band to the p side valence band, means here to here. In ordinary diodes, current produced when applied voltage, we know that applied voltage is greater than the built-in voltage of deflection region. But in case of tunnel diode, the scenario is a bit different, that small voltage which is less than the built-in voltage of the deflection layer is very enough to produce the electric current. So, uh, so this is actually, if we see here, that the electrons are not going this, no need to overcome this deflection layer. With the tunnel directly from N region of the conduction to the P region of the valence band. So this tunneling will create the, or will generate the electric current. However, this we cannot get in the ordinary diode. So if we just that how we are getting this tunneling current or this electric current in the tunnel diode, that first of all, electron no need to overcome this barrier, the opposing force of the deflection layer to produce the electric current. The electron can directly tunnel from the conduction band of the N region into the valence band of the P region. Thus, electric current is produced in tunnel diode. So now this is the how we can generate or see that electric current in the tunnel diode, and we understand that difference between PN junction diode current flow and the normal PN junction diode electric current and the tunnel diode electric current. So now let us see stepwise that how this tunnel diode is working, starting from this diode unbiased, biased with increasing voltage, further increasing. What is its effect? Okay. So very first is that the unbiased condition. That means we are not applying any kind of voltage on it. So uh, when no voltage is applied to the tunnel diode, it said that it is the unbiased condition. So what will happen in tunnel diode? There will be no current flow. Why? Because the conduction band of the N materials overlap with the valence band of the p-type material because of the heavily doping. Both the material is heavily doping. So you can see that this is a line. So because of this overlapping, the conduction band electrons at N side and valence band holes at P side are nearly at same energy level. So when temperature increases, some electrons tunnel from conduction band of N region to valence band of P region. In similar way, holes can tunnel from valence band of P region to the conduction band of N region. However, the net current flow will be zero because an equal number of charge carrier flow in opposite direction. So, if we summarize this unbiased effect of tunnel diode, very first the conduction band of N side overlapping with the valence band of P side, since tunnel diode is heavily doping, and due to this overlapping, the conduction band electron at N side and valence band of P side are nearly at same energy value. So if we now give the temperature, or if we increase the temperature of this circuit, this system, the electron tunnel from the N to P side. So same way the P side holes can tunnel from valence band to conduction band of N region. So since here this number flow of opposite direction is equal, means charge free electrons and holes are equal in opposite direction, so there will be no current flow. So if we see in this that it's indicating there is no current flow in the unbiased condition of tunnel diode. So now see in step 2. Now if we apply the voltage, means if we are giving some bias voltage, if we apply a very small voltage to the tunnel diode, means this voltage is maybe very less than the built-in voltage of the depletion layer, so no current will flow through the junction. Why? So when this small voltage is applying to the tunnel diode, very less than built-in voltage of deflection layer, no current will flow through the junction. However, a small electrons in the conduction band of N region will tunnel to the empty state of the valence band of P region. This will create a very small bias tunnel current. Thus, tunnel current starts flowing with small application of voltage. So, here with very small applied voltage, we can get a very small current. This you can see just voltage current, it is increasing. Very small current is flowing. So if we keep on increasing this voltage, what will happen in next step? Further applying the voltage. When voltage applied to the tunnel diode is slightly increased, a large number of free electrons at N side and holes at P side are generated. Because of the increasing in voltage, the overlapping of conduction band and valence band increased. So if we simplify it, that energy level of n side uh, conduction band becomes exactly equal to the energy level of p side of valence band. As a result, maximum current can flow. You can see that this maximum tunnel current can flow. So after getting this maximum current flow, means while this line is in same, the energy level of n side of conduction band and energy level of p side valence band is equal, then what is happening? Further increasing the voltage. So if we further increase the voltage, a slight misalignment of conduction band and valence band is taking place. So what will happen? Because of this misalignment of this conduction and valence band, since the conduction band of N material and the valence band of P materials still overlap, the electrons tunnel from conduction band of N region to the valence band of P side and cause a small current flow. So now what will happen? Since the current becoming small, or we can say less, so tunnel current start decreasing from this maximum. Tunnel current starting decreasing. So initially where we are not giving any bias voltage, there is no current. So if we are giving very less voltage, less than 2 billion potential, a small amount of current is flowing, and while we are increasing the voltage, the maximum tunnel current we are getting in this region. And where we see that when we are getting the maximum current, there our alignment of this conduction band level and this valence band of level p side is in same line. So further increasing the voltage, this misalignment is occurring in the conduction band of n side and the valence band of p side. Then as a result, this current amount is suddenly drops, or suddenly, but still current is flowing. So the tunnel current starts decreasing. So now if we apply the voltage very largely, so if we apply the voltage very largely, we can see like a graph. Okay, so what is happening while we are increasing this voltage very largely, that if we apply the voltage is largely increased, the tunnel current drops to 0. At this point, the conduction band and valence band no longer overlap, and tunnel diode operates in the same manner as the normal PN junction diode. So if we forget about this part, and if we just take this part is basically similar like normal PN junction diode, right? So if we summarized this, that tunnel current under very high voltage, that if the applied voltage is very greater than the built-in potential, obviously here the the applied voltage amount is very high than the built-in potential. So the regular forward current will flow through the tunnel current. We know this is in general, that when the applied voltage is greater than the built-in potential. So we see the case for the normal PN junction diode, that when applied voltage is greater than the built-in potential of the deflection layer, the current flows or flows uh, increasing way. So similarly here, that obviously this very high applied voltage, that means this applied voltage is exceeding the built-in potential. So regular forward current flows through the tunnel diode. The section where the current decreases here as voltage increases. So voltage is gradually increasing, but here you can see that current is slopes down. So this is known as the negative resistance region. This region is the key characteristics of the tunnel diode. So this behavior, or this can be this special behavior of the tunnel diode can make it used in amplifier or in oscillator. So basically what happening here, that we are applying voltage is much greater than the built-in potential of the deflection layer. The regular forward current flows through the tunnel current. The portion, this portion actually, in the if the current decreases while voltage increasing, is the negative resistance region of the tunnel current. So this negative resistance region is the most important and most widely used characteristic for tunnel diode. This tunnel diode operating in a negative resistance region can be used as amplifier or oscillator. So this is very interesting uh, and very important key features of tunnel diode. So some of the application we already go through while we are went through this lecture. But if we summarize that what are the advantage, disadvantage of tunnel diode, let us summarize it. That tunnel diode is very long life, high speed operation. It have very low noise and low power consumption. These are very our expectation from any of the diode while we using in electronic technology community, that we should be low power consumption, low noise, very high speed operation is appreciated to for that uses. At same time, that since the we see that tunnel diode structure is bit sophisticated. So in fabrication actually it has some limitation, that it cannot be fabricated in a very large numbers, and input and output are not isolated from one another. So these are the very crucial points for disadvantage point of the tunnel diode, because it is a two terminal device, so the input and output not isolated from one another, and its application it use very large in the logic memory storage devices. Tunnel diode are also used in relaxation oscillator circuit. It also used in very ultra high speed switch devices. Also it uses in FM receivers. So now let us move in this that next, that is the uh, last diode, advanced diodes of this series lecture, is the Schottky diode. So as of now we have discussed about Varactor diode, Avalanche diode, then pin diode, tunnel diode, and now we are moving the our in aim the last is the Schottky diode. So what is Schottky diode? It is also a semiconductor diode, but it is more special than which we have discussed in early. It is basically a metal semiconductor diode junction. So that has very less forward drop than the normal PN junction diode, and can be used at a very high speed switching applications. So as we know that normal PN junction diode, uh, P-type semiconductor and a N-type semiconductor used to form the normal PN junction. So basically we can say that P-type semiconductor is sandwiching with the N-type semiconductor. So a junction is formed between both the material, and this is called the P-type junction, or is we can say also the PN diode. So basically in the Schottky diode, that it is, since we share the metal semiconductor junction diode, so this normal PN junction, that P type and N type, and this is called actually the junction, and because of this junction we can name it as PN junction. But for case of Schottky diode, metal mostly made of with aluminium or platinum replaced the P type, type material. So basically here we'll have this Schottky diode made of with a N type layer and a metal. So this metal can be aluminum or platinum. And this junction will say, since this side metal and this side the semiconductor, that MS junction. So in Schottky diode, the metals, basically we know that it is basically made from the aluminium or platinum in place of P type. The and also this diode is the semiconductor diode is named after the Walter H. Schottky. It's also known as the Schottky barrier diode or surface barrier diode or hot electron diode. So it is mostly and widely used in the radio frequency applications. So just this is the typical symbol of this diode. So you can see that this is indicating that this is a Duncan diode, and you can see that this line is a bit different from the normal PN junction diode. So when basically this aluminum or P-type metal is joined with the N-type material, a junction is formed that is named as metal semiconductor junction. So you can see the metal semiconductor junction formed between a metal and a N-type semiconductor, which will create a barrier or deflection layer. So this is specially named as the Schottky barrier. So this Schottky barrier actually can switch on and switch off faster, much faster than PN junction diode. Also, it produces less unwanted noise than PN junction diode. it have very two characteristics like useful in the very high switching device performance. So let us let us discuss about this Schottky diodes difference between the normal PN junction diode. So basically Schottky diode is switch on and off is very much faster than the PN junction diode, and Schottky diode actually produces very less unwanted noise than the PN junction diode, and also in when sufficient voltage is applied to the diode, the Schottky diode, the current start flowing in forward direction. Because of this current flow, a very small voltage loss occurs across the terminal of the Schottky diode, and this loss of voltage is known as the voltage drop. A silicon diode that has a voltage drop around zero point 0.6 to zero point 0.7 volt, while the Schottky diode have a voltage drop of zero point 0.2 to 0.3 volt. Voltage loss or voltage drop is amount of voltage that wasted to turn on a device. So we can say the voltage loss of or voltage diode of Schottky diode is much less than the normal PN junction diode. And also the in voltage need to turn on for the Schottky diode is very similar like germanium diode, but germanium diode are rarely used because of switching speed of germanium diode is very low as compared to the Schottky diode. And this Schottky diode actually that here were that generally that normal PN junction diode is anode and cathode we are defining from the P and N type of semiconductor, but here we can see that in place of P we have the metallic part or metal layer. So basically the metal act as a here anode and N type act as a cathode. So because to get this anode part, we are replacing P side, not the N side. So important to remember that this is also one of the reason to replace P type by the metal contact. So this junction formed, this MS junction is this is the unique difference between all the special type of diodes to compare to other diodes to the Schottky diode and normal diode. So this junction is sometimes also called as like MS junction as here mentioned. And so basically this is nothing but the junction or joint or sandwiching part in between metal and the N type. And while we PN junction semiconductor, we are saying this junction and called as a PN semiconductor. So that's why sometimes it is also called the Schottky barrier diode or surface barrier diode or Schottky diode. So uh, yes, so this is the, you can see that metal there is lot of holes here, and inside there is the electrons. So in these junctions these negative ions and the positive ions actually procedures of this uh, diode formations means this same Schottky diode formation is the same. So we can, if we say that what is the Schottky barrier, so it is, we can define as that it is nothing but the deflection layer formed at the junction of a metal and N-type semiconductor. And in simple word, we can say that Schottky barrier is the potential energy barrier formed at the metal and semiconductor junction. The electron have to overcome this potential energy barrier to flow across the diode. So another aspect of this is that semiconductor rectifying metal semiconductor junction forms a rectifying Schottky barrier. This rectifying Schottky barrier actually, that is nothing but this barrier, is used for making a device known as the Schottky diode. The non-rectifying metal semiconductor junction forms a non-rectifying barrier. So this is the rectifying barrier and this is the non-rectifying barrier. So now let us see that it is very curious to know that what is the difference of energy band of Schottky diode as compared to normal diode or others. What is the main effect of this metallic contact with this semiconductor? So we know that for the this metal, and the in case of that this is defined as the work function, and for semiconductor. So here in particular for n-type semiconductor, this work function is defined as Fermi energy to the zero level, and this is the conduction band and this is the valence band. So this EF is basically here Fermi energy and E naught, it is the vacuum level. So work function actually basically nothing but the difference between the energy in vacuum level and the energy of the Fermi energy. So for n-type semiconductor, it lies the Fermi energy in between conduction band and valence band. So Fermi energy to this vacuum level energy is basically defined as the work function of the n-type semiconductor. So actually, one of the important characteristics of Schottky barrier is that Schottky barrier height. That barrier height of this Schottky actually depends on the combination of the semiconductor and the metal. So when the Schottky barrier height, as we discussed in last slide, that height is ohmic contact, then you can say those are the non-rectifying barrier, is very low, whereas the Schottky barrier height, which is non-ohmic contact, is very high, which is also known as rectifying barrier. And in rectifying barrier, actually the barrier height is high enough to form a depletion region. So depletion region is very present in the non-ohmic diode. So this ohmic and non-ohmic contact will gives the linear current voltage curves or non-linear current voltage graphs. So this let us see that in the what is the effect of this energy level, how we can define or how we can analyze it. This vacuum level is actually nothing but the energy level where the that level of the electrons that are outside the material. The work function of any of the material is defined as that energy required to move an electron from Fermi level to vacuum level. That means this EF is nothing but the energy required to move an electron from Fermi energy to vacuum level. So we know that work function of a metal is greater than the work function of a semiconductor. We can see from this that this value is very high compared to this n-type semiconductor, and therefore the electron in type of semiconductor have high potential energy than the electrons in the metal. So energy level of metal and semiconductor is different, and it is here we are defining that we know that electron in the higher energy level have more potential energy than the electron in the lower energy level. So electron in the p-type semiconductor have more potential energy than the electron in metal. So energy level diagram of the metal and n-type semiconductor has drawn here. So we can see from here that uh, when the metal is joined with the n-type semiconductor, because this energy work function and level is different, this device create or diode create is named as Schottky diode. The built-in potential for Schottky diode is given the difference between the work function of metal and semiconductor materials. So now let us see that with this energy built-in potential difference and different two contacts, how these diodes work in bias condition and with that increasing bias voltage. So let us first discuss that how it works in the unbiased condition. So this is basically the um, schematic diagram of metal and n-type semiconductor behavior in the unbiased Schottky diode. As usual here, these are the defined as electrons, and these white spots are is holes, and this is the in metal and n-type semiconductor. This dotted is the depletion region, and this is the junction. Here it is creating negative ions near to metal side, and near to n side it is creating the positive ions. So basically when this metal joined with the n-type semiconductor, the semiconductor band electrons, these free electrons in the n-type semiconductor will move from n-type to metal to establish an equilibrium state. We know that when natural neutral atom lose an electron, it becomes a positive ion. Similarly, when a neutral atom gains extra electron, it becomes the negative ion. So near the junction, we can see here negative and positive ions. The conduction band electrons of free electrons that crossing the junction will provide extra electrons to the atom in the metal. As a result, the atom in the metal junction gains extra electron, and atoms in the inside junction lose the electrons. So the basically the atom that lose the electron in inside of the material will become the positive ion, and whereas the atom in the metallic side, this side that gains electron would be at the metal junction will become the negative ions. Thus positive ions are created n-side junction, and negative ions are created the metal junction. These positive and negative ions are nothing but the depletion region. So since that we know that in the metal there have a lot of free electrons, the width over which these electrons move into the metal is negligible. Compared to the with other semiconductors, so the built-in potential or potential voltage is primarily present in the n-type semiconductor. So built-in voltage barrier seen from conduction band of electron or electrons of the n-type while trying to move to the metal. So now let us see that while how it works in forward bias conditions. That if positive terminal of battery is connected to the metal and negative terminal of the battery is connected to the N type of material, then Schottky diode is said to be forward bias condition or forward bias connection. So when this forward bias voltage is applied in the Schottky diode, a large number of free electrons are generated in the N-type semiconductor and metal. However, the free electron in the N-type semiconductor and metal cannot cross the junction unless the applied voltage is greater than 0.2 volt. So if the applied voltage is greater than 2 volt, the free electron gains enough energy and overcome the built-in potential of the depletion region, and as a result electric current start flowing to the Schottky diode. If the voltage is continuously increased, the depletion region becomes very thin and finally disappear. So now let us look that what is in reverse bias. So in the reverse bias, this is nothing but that negative terminal of the battery is connected to the metal side and positive terminal of the battery is connected to the N side. Then what is happening here, that if we connect that negative terminal of the battery to the metal and positive terminal of the battery to the N-type semiconductor, the Schottky diode is now in under forward bias. So when forward bias voltage is applied to the Schottky diode, the depletion width is increasing. So we can see that gradually in the forward bias it was reducing, and up to certain time it is disappearing. But here this width of the depletion region is gradually widen the region thickness. So as a result, the electric current stops flowing. However, a small leakage current flow due to thermally excited electrons in the metal. Because we know that we can get a small leakage current due to that thermally excited electron in the metal. So if this reverse voltage now continuously increase, the electric current gradually increase due to weak barrier. So if this reverse bias voltage is largely increased, sudden rise of electric current takes place. This sudden rise in electric field, rise in the electric current causes depletion region to break down, which may permanently damage the device. Because of this metal and semiconductor junction. So if we summarize the forward and reverse bias, that until the applied volt for the forward bias, until the applied voltage is zero point 0.2 volt, the until the forward voltage is very less, the cannot cross the junction this charge carriers, and there will be no flow of current. But if the applied voltage is greater than 0.2 volt, that is small amount of voltage we applied, the free electron gains energy and overcome the built-in potential, and as a result we can get the electric current starts flowing to the in the Schottky diode. And if the applied voltage is continuously increasing, then this layer becomes very thin and finally it will disappear. However, in case of forward bias, if the reverse in the reverse bias conditions that we are applying the voltage uh, is applying, then the deflection layer is becoming thick, that means increasing, and as a result the electric current will be drops, stops flowing. However, very small leakage current we can get due to thermally excited electron in the metal side. And then if we further increasing the applied voltage, the electric current gradually increase due to the weak barrier. And then if we increase furthermore, a sudden rise of the electric current takes place, and this sudden rise of the electric current cause deflection region to break the region or permanently damage the device. So now see how is IV characteristics of this diode. So this is the IV characteristics of Schottky diode. So you can see that this is the forward characteristics and this is the reverse bias. So it is hugely different than the other semiconductor diodes actually. So this vertical line in the figure, this is representing the current flow in Schottky diode, and the horizontal line representing the voltage across the Schottky diode. So this is, you can see that except this part, sudden drops or sudden rising, it is normal, just almost similar like the PN junction diode. However, the this forward bias voltage drops is very low compared to the PN junction diode, and the this forward actually voltage drop of Schottky diode is around 0.2 to 0.3 volt, and where is the forward this voltage drop for a silicon diode, normal silicon PN junction diode is around 0.6 to 0.7 volt, and if the forward bias voltage is greater than 0.2, electric current start flowing to the Schottky diode, and also in the reverse saturation current occurs at very low voltage as compared to the normal silicon diode. So if we make a comparison with the silicon diode and PN junction diode, that what are the different features we are getting here, that in Schottky diode the free electrons carry most of the electric current, but and holes carry very negligible current. For Schottky diode is a unipolar device because here the current is mostly flowing due to the free electrons. And in PN junction diode actually both free electrons like and holes both carry the electric current. So PN junction diode is a bipolar devices. And we see from here this IV characteristics and forward and reverse bias concept, that a reverse breakdown voltage of Schottky diode is very small as compared to PN junction diode. In Schottky diode, the deflection region is absent or negligible, where the PN junction deflection region is present and it is very distinct. And also the turn-off voltage of a Schottky diode is very low as compared to the PN junction diode. So these are the different between PN difference or comparison between PN junction and the Schottky diodes, and also most importantly the in Schottky diode the electrons are majority carriers in both metal and semiconductor, because we know that in the n-type semiconductor the electrons are the majority carriers and metal obviously is the electrons, free electrons. In PN junction the electrons are majority carrier in N region and holes are the majority carriers in P region. So these are the distinct and different features of semiconductors and normal junction diode. Let us look application of also another important application of Schottky diode is low forward voltage drop and low turn on voltage. So basically, we turn on voltage for Schottky diode is very small as compared to PN junction diode. The turn-on voltage of Schottky diode we have seen that is around zero point 0.2 to zero point 0.3 volt, whereas for PN junction diode it is zero point 0.6 to zero point 0.7 volt. So applying a small voltage is enough to produce electric current in the Schottky diodes. So it have various advantages like it is low junction capacitance, very fast recover time, high current density, low forward voltage drop or low turn on voltage, high efficiency. It operates at high frequency and also less unwanted noise than the PN junction diodes. So these are the various advantages and applications for Schottky diode. However, it has very large reverse saturation current, and Schottky diode produces large reverse saturation current than the PN junction. This is the disadvantages of Schottky diode. So hope it will helpful to you. And this was Schottky diode was the last as per outline of this lecture series. Thank you. Thank you very much.